I'm David Orrell, and I will be talking about quantum Judder for financial engineers. And the idea for this talk came about from in the July issue of Wilmott magazine. I did a dialogue with Paul, and he mentioned that I've been blathering on about a quantum finance model for ages now, and I realize it's true. I've been giving talks each year at the CQF for the last 5 years on the quantum model, so I thought this time I'd change things a little bit and focus more on empirical results. So I'll start by talking a little bit about the model, then get on to predictions, validation, implications, and engineering. I know a lot of people, when you hear quantum finance, you're going to be thinking this is extremely complicated, but I just saw the presentation a couple of hours ago about retirement planning, and I think that quantum finance is actually kind of simple in comparison. Okay, so the classical model, which we're all familiar with, assumes equilibrium and is static. Perturbations are due to random views. And the log price change x, therefore, follows this normal distribution. So the question that I wanted to sort of address is, how can you build dynamics into this picture? And one way is to view the normal probability distribution as being the product of a linear entropic force. So you can imagine this like a kind of a spring-like force which corrals the probability into the center. When you think like linear force, that suggests oscillatory dynamics. We know that price does not oscillate. But when you have dynamics and probability together, then an appropriate mathematical framework is quantum probability. If you apply that to this force, you get a quantum harmonic oscillator. You have a complex valued wave function which rotates around the imaginary axis. So it's a dynamic system now. And the squared amplitude of that in the ground state is just that same normal curve. So we're going to use this to represent the system over a period like t, and scaling a little bit like in the classical model means that the distribution is going to be a function of z, what we'll call z, which is x divided by the square root of t. And the volatility over any period ultimately reflects the bid-ask spread, which gives a fundamental level of uncertainty. A price change over the period t perturbs the oscillator and puts it into what's known as a coherent state, and the corresponding probability distribution is an oscillating normal curve. So you kind of think as a normal curve on a spring, kind of bouncing back and forth. So this model was first developed to study price impact, so that linear restoring force is what explains the square root law of price change, but it also affects the variance, and over a period this depends on a quadratic fashion on the displacement z. When I was putting these slides together, I was reminded of these alcohol pop ads from around the year 2000. And so there were some people at a party and they're enjoying a drink, and then suddenly they all experience this kind of strange vibration feeling. And this guy shows up and says, "Let me explain, I'm a freelance scientist. Technically it's known as a judder." And I always thought this idea of a freelance scientist was kind of amusing because we know scientists aren't supposed to be freelancers, though it did eventually become my job description. Okay, so what does this quantum model predict? Well, there's two main things. So the first, which is calling Q-Variance, is that variance is quadratic in z, which again is x divided by the square root of t. And the second is that the distribution of z follows a particular sum of Gaussians, which we're calling the Q distribution. And both of these follow from the basic properties of the quantum harmonic oscillator, and they're mutually consistent. So that's Q-Variance on the left and the Q distribution on the right. So there are a couple of things which are confusing about this. One is that in the classical model, prices at equilibrium, volatility is caused by market price adjusting to random flow of news. So in dynamical terms, the model is basically zero order in the sense that it assumes equilibrium. So this ties into the whole story about efficient and stable markets and so on, which is a great narrative. In the quantum model, on the other hand, volatility is caused by transactions across the bid-ask spread, which again is a fundamental level of uncertainty. Also, in dynamical terms, the model is first order in the sense that it assumes a linear restoring force. So now you have this picture of uncertain and unstable markets, which might not sound quite as attractive. Another even more confusing fact is that in the classical model, we break time down into discrete steps. Price change follows some version of a random walk. But in the quantum model, we model the probability price change over a complete period. So instead of a time series, we have a probability distribution at some final time t. And then there are other problems with the quantum model, and I've represented them here by this evil Judderman character who appeared in the follow-up Met's Alcopop campaign. And this guy tempted travelers with Alcopops and turned them into puppets. Very scary. So some of these things like mathiness, physics envy, misunderstanding of deep quantum ideas of popular one, and so on. But there's really a much bigger problem with this whole approach. And it's interesting that hardly anyone spots this, even when they're given a lot of time. And this was actually true of me as well. It's got to do with this equation, which is the Q-Variance equation. So in words, this says that the variance calculated over periods of length t equals a base variance plus a quadratic term in z. So if you look at that little inset diagram there, you've got x is the log price change over the period t, z is equal to x divided by the square root of t, and sigma squared is the variance. It's calculated from those 5 points. This is t equals 1 week. And so that gives you 1 point. And then when you get lots of those and then you average, you bin them for a particular z and take the average, that will give you the variance as a function of z, which is this Q-variance thing. Okay, so maybe you're feeling confused, maybe you think you've seen this before somewhere, or maybe just wondering what the problem is. Well, the problem is, where's the parameter on the quadratic term? So the 2 in the denominator is not a fit. It's there for kind of the same reasons the 2 in the exponent. So they're like, if you integrate z, you get z squared over 2. It's kind of like that. And since when in finance can you have a term without a control knot? This is like a suicide move in a game. Remember, this is supposed to apply for kind of any asset, but also for all periods, like a day, a week, a month, a year, whatever. Remember, z is equal to x divided by the square root of the period. So this is very easy to falsify. Also, it's not a small effect. The total variance, you can check by taking the expected value of each side, is 2 sigma naught squared, so twice the minimum. So it's this big effect. You should be able to see it. Now, financial time series have been studied for over centuries, so surely this would have been discovered already. And yes, where is this in the literature? Well, if you take a look, and we didn't come back to this, but it appears to be nowhere. Okay, so we've got a large effect. It applies to all periods and assets, never been seen, sounds like a real winner, but let's check it anyway. Okay, so this is an online app, which I'll put the URL up again later, which allows you to check this for a number of stocks. So here we've got S, the second column there is the price of the stock, in this case 3M. Y is the log daily price change. X is the log price change over the period T, which here is 1 week. We're also subtracting off the average drift. So that's like a small amount just to remove that kind of constant drift effect. Z is X divided by the square root of T, so it's like you're normalizing it for the period. And V is the annualized variance over the period. And that would just be like those 5 points. Okay, and so if we plot, if we do this for lots of, the whole time series. So it's starting here with a dummy random walk series. And looking at periods T of 1 to 26 weeks. So each of these points represents variance over a single period. The grayscale shows a period length, so the black points are for 1 week. Blue line is the mean, so that's like sigma squared of z. It's the variance as a function of z, and it's flat. You can also see in the right-hand side, I've broken it down into 1, 2, 4, 8, 16 weeks. You can see them separately, but it's always flat. Red line is Q-Variance. They don't agree. There's no kind of weird Judder thing going on here. Okay, how about a jump diffusion model? So it turns out that you can calibrate a jump diffusion model so that it works for a particular value of t. The process is described in this Journal of Drifters paper. So here I've calibrated for t equals 1 week, and you can see on the right there that it works for 1 week. But by the time you get down to 8 weeks, it's all sort of washed out. And that makes sense. This is because random effects, kind of central limit there, and they just sort of wash out, and the net effect becomes increasingly normal. And you can see pretty easily that no version of a kind of like a typical random walk or something like that's going to work. Okay, so now let's try an actual stock. So this is 3M, got about 33 years worth of data. And now you see that the pattern is holding for all t. So on the right and in the center, the red line is now a good fit to the, pretty good fit to the blue line. Try a different stock from a different sector, Lily, similar result. AIG, so that the red line, the parabola is just shifting up or down, it's not doing anything else. Amazon has higher volatility, so it shifts up. Can try combining all of the stocks together so you get more points, and now that you see the red line is a bit of a better fit to the blue line. You can look at other stuff as well. So this is Bitcoin versus US dollars, it shows Q-Variance. This is kind of an interesting one. It's the 5-year treasury yield. So this is sort of the opposite of Bitcoin in the sense that yields are range bound. It's a very different kind of behavior, but you still get the same kind of Q-Variance effect. This is the S&P 500 index. So this is the biggest market for options trading. So you would hope that it would work here. I've added a very small offset just to make the fit essentially perfect kind of in that central region there. Now, this is not a stock, it represents an average of stocks, and that's why the volatility is lower. And really a better test is that if the quantum model is a good first order approximation, then it should correctly predict the average variance over many stocks rather than the variance of the average. So we'll use the stocks which have been in the S&P 500 for 75% of the time since 1992. This gives you a minimum of about 25 years each. This is a pretty large data set for 355 stocks, contains about 2.9 million points. Plot variance is a function of Z for each of these stocks, and then take the average over all of them. So remember, because there's no parameter on that quadratic term, this can be falsified, which is quite rare in finance. Okay, here are the gray lines represent those 355 stocks. Variance is a function of Z. So if we take the average of those, we get the blue line, and then overlay the quantum model, again with a very small offset, just to take account for any little asymmetries, and the fit is essentially perfect. Okay, how about the Q distribution, which I mentioned? So this is it's a particular Poisson weighted sum of Gaussians. The sort of full story is in these works, and as I'll discuss later, it's not some other sources, but basically it's again a very simple model in the sense that there's only one scaling, there's only one parameter, one free parameter, which is sigma 0, which just kind of just scales everything. Okay, so here are the distributions for our 355 stocks. The black line is the average, and these, because the stock, just if we want to see the same shape, we can scale each stock so that we have roughly the same standard deviation, and that gives us this, and the dashed line here is the quantum model. So again, the agreement is excellent. Okay, so for most cases, and you can just check this yourself, the quantum model is a good first order approximation to asset price behavior, and in particular, it correctly predicts Q-variance and the associated Q distribution. For these two figures, the solid line is the average of the 355 stocks, and the dashed line is the quantum model. Okay, this is really quite strange. As Paul Wilmott said, and he was really the first person to notice how weird this was. At this conference, a volatility conference a few months ago, I've sent it to experts to look at, and nobody has seen this before. Nobody can explain it. Q-variance was predicted using a model. It applies for all assets and periods. It involves no parameter in the quadratic term. It's a large effect. It has obvious implications for things like option pricing. We'll get into that. It's never been previously reported or predicted, and no alternative explanations have been suggested following requests to experts, forums, conference attendees, readers, and so on. This raises some questions. Is it still physics envy if the price change behavior of stocks follows the harmonics of a quantum harmonic oscillator? Okay, this is being facetious, but it is weird that you can look at the average of these stocks and these numbers pop out. Why was Q-variance not noticed? After all, the volatility smile was a clue. And why is it still so hard to see? And finally, why should I care? These things always come out in the wash, right? Well, for a start, prices do not follow a random walk. We saw that the random walk thing doesn't have the right behavior. And I can kind of hear everyone saying, we know that financial time series have been studied for many decades. We know they're not a perfect random walk. But no, they really do not follow a random walk, nor do they kind of follow a random walk. A random walk is the wrong model in the same sense that a parabola is not a straight line, it will not work. Here's your classical model, a random walk. Here's a real stock. They don't look the same. If you zoom in a bit, you see in the classical model, all those dots are symmetric around the blue line. In reality, the dots are all kind of like crunched together down at the bottom. You zoom in even further, you see that the classical model has no smile, but the reality has a smile. Okay, so the quantum framework accounts for dynamical effects on probability. Models based on equilibrium misimportant structures has implications. An example is option pricing. So the Black-Scholes proof assumes a log normal random walk. The equations therefore do not apply to a system with Q-Variance. So if you look at your log normal random walk equations, got a sigma, but what sigma? And again, I can hear everyone saying, so what? Everyone knows the Black-Scholes model is not perfect. This is why researchers have been modeling implied volatility for decades. And that's kind of true. But let's back up. How do you find the correct volatility to use for a given log minus x and time to expiration t? Well, the answer should reflect the expected payout of the option. And three possible methods suggest themselves. One, use a mathematical model. Two, find the average volatility that traders have used. And three, find the volatility which actually matches historical payouts. And you think that actually three should really be maybe the starting point if you're trying to calibrate a probabilistic model to get the expected payouts. But anyway, let's do the normal mathy thing, which is to start with a model. So the classical model assumes a normal distribution with constant volatility. The Q distribution, however, implies that we need to use a volatility given by this equation, which is basically a flattened version of Q-Variance. It's described by a single parameter sigma 0, and the curve looks as this V-shaped thing on the right there. Okay, could this be related to the implied volatility smile? Well, again, this is nowhere in the literature. In fact, according to no arbitrage, implied volatility scales with the square root of x in the wings. Here we're saying I should asymptote to 0.32z, which is a linear, also weirdly specific, since when in finance is there a formula without any control knob, 0.32? But let's check it anyway, and we'll look at a big picture of a range of x and t. So here's our implied volatility surface for our model. So here x is log moneyness in this case, and t is time to expiration, and this is our model. There's only a single free parameter, sigma 0, q is just a number, and that's set. So this is an incredibly simple model. I just the parameter just kind of lifts this up or down a bit. On the right, you can see it's plotted versus z, so now it's a 2D thing, and it's this V shape, which is linear in the wings with a slope of about 0.32. So how does this compare with, well, first of all, implied volatility? Well, here we determine that the average, so we take 17 years worth of SPX data, average implied volatility of each x and t, and we get a shape that is strongly similar. But you can see from the top right, it's not exactly the same, so there's some deviations. Puts, for example, especially in the center there, a bit more highly priced, for example, but the slopes, again, and the wings are about 0.32. Okay, and how about the payout implied volatility? So again, this is computed from taking the volatility which matches the actual average payouts. But you have to include a minimum cost in the wings. Options are never free. So that's like another example of that bid-ask spread coming in. You do that and you get something which again is very close, not exactly the same as seen in the top right there. Okay, so the volatility smile, it's a complicated phenomenon. In classical finance, it's usually viewed as a logical inconsistency caused by irrational behavior. After all, in the classical model, a stock can only have one volatility at a time, right? But from the quantum perspective, the smile is largely due to the fact that traders know about quantum judder. They just don't know they know it. Okay, so the quantum model predicts three new properties: Q-Variance, the Q distribution, and a main structural component of implied volatility. In the classical model, these are all constant, normal, flat, and so on. Okay, so what does the quantum model not explain or predict, and what makes no sense at all? Well, One thing is that, as mentioned, classical finance works by breaking time down into discrete steps. And you think about sort of how most things are done in science. We sort of break things down into the parts. So here the difference is that the quantum model treats the period as t as a whole. So one question is, how do you produce a time series which follows Q-Variance over all timescales? And this is an interesting question, and come back to it later. But note that what counts for vanilla option prices anyway is just the distribution. Now, of course, to calculate option prices, we do need the growth rate mu. And classical theory allows us to set mu equals r. What about the quantum model? Well, let's back up again. The Black-Scholes proof used no arbitrage to show that only the risk-free rate R matters. In other words, you can outsource the job of predicting the growth rate to the market for treasury bills, which is great. Option pricing, therefore, only involves a single free parameter, the volatility. Even better, in theory, the hedging process made it possible to eliminate all of the risk. I just find it ironic that people think that the quantum model is counterintuitive, when here's the classical model, which is saying things which are deeply surprising. As J.P. Bouchot said, there are two surprises. One is that the option price does not depend on the expected average return, and the other is that through hedging, we can take no risk at all. And these remarkable claims were key to the development of classical finance. As Manuel Derman said at this recent conference, if you can hedge away all correlated risk, and you can then diversify over all uncorrelated risk, then you should expect to earn only the riskless rate. This sentence leads to modern finance. So it kind of boils down to mu equals r. But no arbitrage only makes sense if you assume a random walk and ignore the bid-ask spread. So for example, the Black-Scholes proof assumes transaction costs are zero. In the quantum model, the bid-ask spread is the cause of volatility. Setting it to zero is the same as assuming volatility is zero. The proof, therefore, just doesn't apply, which means that arbitrage is allowed, which is useful since, of course, it is the business model that much of the financial sector. Now, the quantum option pricing model, and the details are given in this Journal of Derivatives paper, uses only two parameters, sigma naught and mu, which is very parsimonious given the complexity of the problem. But sadly, mu does not equal r. But really, why should it? I mean, if I'm buying options on the S&P 500, I don't consult the daily risk-free rate. It doesn't really seem too relevant. Now, again, I can imagine this idea that Q-Variance somehow invalidates all of classical finance and seems crazy and boring and sort of feel the eye roll. People have been saying this for forever, but if you sort of think, okay, these ideas have held up for such a long time, efficient market hypothesis being described as the best established fact, the best tested proposition in all social sciences. Black-Scholes is the most successful theory, the most widely used formula with embedded probabilities in human history, gave birth to the important field of financial engineering. In the current issue of Wilmott, maybe a sort of slightly tongue-in-cheek, but from a theoretical point of view, we have proofs for almost all results in mathematical finance, meaning that we can replicate them. And that's true in that classical world, the world of the classical random walk. But now try proving it for a system with Q-Variance. This doesn't really seem to work. And DS here is not even really a thing. I mean, what is DS during a crash or even just a transaction? What dynamics are there? And so on. Okay, so I'm going to ask that or suggest that we all just try to forget about theory for a while here. And I know this is a tough ask. This is a very theoretical kind of quant finance crowd. Be especially difficult here if you're still worrying about all the quantum aspect of this. But if you are here, that's okay. Just kind of remain there for a bit. I think for the rest of us, though, I would like to end all of the quantum component of this talk and look at it from more of an engineering perspective. So we speak of financial engineering. We have, I guess, laboratories and centers for financial engineering. You can do a master's degree in financial engineering and so on. And so, okay, let's take this seriously and look at this from an engineering perspective. Now, I am not a financial engineer. As mentioned, I am a freelance scientist. However, I did start off, and my first science and engineering job was at Oxford Instruments. So we were working on a compact synchrotron project for IBM. And part of this involved calibrating Hall probes to measure the field of a high-power superconducting magnet at cryogenic temperatures. And we expected that the field would have a roughly linear relationship with the voltage, but in reality, the signal showed Judder-like fluctuations as voltage increased. And the effect was consistent, so we could just correct for it by including a term, the sort of oscillatory term shown in that figure at the bottom. And later, an IBM physicist showed that the fluctuations were due to quantum effects, which was very interesting, but the theoretical explanation didn't actually make any difference to the calibration or the course of the project. So what are the parallels to financial engineering? Well, I think one way to look at it is that financial engineers build structures that are based on a substance known as volatility. And it turns out that volatility reacts in a particular way to stress. It expands, which was not anticipated by models. The effect is both large, like it can double or more, and systematic. And models will therefore not behave as expected, but errors can be predicted. So some examples, Black-Scholes model is structurally incorrect because it's missing that parabola. Another is the VIX algorithm. I talked about this a couple of years ago at Black-Scholes talk, and this is a key measure of volatility which systematically overestimates realized volatility by about 40%. And when you kind of look into the guts of the model, it's not hard to see why. You got sigma squared being equal to all the strike-dependent stuff on the right. What's sigma? And then anything that relies on no arbitrage, like options at extreme strikes and so on. Now, of course, finance is not really the same as engineering. The role of models often seems more about creating some kind of narrative, usually to do with efficiency, rationality, or optimality. But engineers have codes which apply also to finance. And the question that comes up all the time is how to address model error. And a first step is transparency. As the modeler's Hippocratic Oath mentioned, you need to make explicit the model's assumptions and oversights. And if that z squared over 2 term isn't in your model, then it's an oversight. Also, where do you think quantitative finance will be in 2030? So t equals 5 years. Will universities teach a theory where volatility is constant if everyone and their AI knows it very systematically by a factor of 2, or a theory where mu equals r? And maybe they will. Classical finance assumes equilibrium and practices it, but what about financial engineers? Well, in the sort of normal scientific process, typical things, you start with a model, you make a prediction, validate it. Replication is an important stage, and that's the subject of the current issue of Wilmott magazine. I think that's where we are with this now. And then you get on to like implications, new ideas, and so on. Just looking ahead, some open questions and topics for financial engineers. One would be to produce a time series which is consistent with Q-Variance over all periods. Marcus managed to do it. Another is to develop an alternative to VIX, which works when variance is an offset parabola. As mentioned, the current version does not work. Devise options trading strategies which exploit Q-Variance. Paul mentioned at this volatility conference a few months ago that we'd be playing around with this sort of experiment on this, calling it the quantum fund because it's the smallest hedge fund in existence. Another thing is that you got ideas coming in from quantum computing now into finance, and so there are obvious synergies which are interesting to explore between that and modeling finance as a quantum system in the first place. But the main thing is just very simple. It's just that Q-Variance, and you can test this for yourself using the app or just using your own data. It's a significant empirical effect, and therefore you might want to include it in your models. Okay, thanks very much. So that's the, I've got a list of some further readings. So there are some papers which are recent papers which has come out this year. Got a journal of Quantum Economics and Finance, which publishes stuff related to this stuff, and be a new book coming next year from MIT Press on the quantum stock market. And this is the URL for the Q-Bar app, which if you want to have a look at that and try testing some of these things for yourself. Okay, thanks very much. And if there are any questions.